So what we're doing for this set of notes is we're going to talk about Chapter 7. This is kind of the first part. And we're going to start off by talking about linear regression and residuals. I'm going to highlight a couple terms. So a residual is how far our observed point is from the predicted value. So the way we calculate residuals, a residual is equal to observed minus the predicted. And essentially what happens is this is my prediction line. This is my line of best fit. Okay? This point right here, change colors, is above that line. So this is the residual, how much above that line it is, okay? This point, this point right here is below the line, but this is the residual. Okay, if you're above the line, you're going to have a positive residual. If you're below the line, you're going to have a negative residual. When you have positive residuals, what's happened is that this prediction line is an underestimate. So when your residual is positive, the prediction is an underestimate. So positive resid is an underestimate because they underestimated what the actual was, okay? And if you have a negative residual, it's the same idea. It's down below it, so that means that they overestimated. So it's an overestimate. So for different situations, you're going to want to be a positive residuals, and sometimes you're going to want to be a negative residual. So you have to kind of think about what the scenario is. Do you want to have a higher value than predicted, or do you want a lower value than predicted? Okay. All right, line of best fit is actually the line that has the smallest sum of the squared residuals. It's also known as the least squares regression, least squares regression, and that is the LSR. And what it does is it minimizes the residuals. It's also known as the best fit line. So you're going to see about 3 or 4 different types of words that mean the exact same thing. So line of best fit, linear regression, LSR. All of those are the same thing. Okay? Now, this is my line of best fit. It minimized my squares. The reason you have to square it is if I don't square it, a positive residual and a negative residual, when I add them up, it's going to just cancel each other out. So by squaring it, it takes care of that and it doesn't cancel out negatives. All right, so when you write a formula for line of best fit, you have to put it in context. And so it's the y unit. So if I'm estimating height, it's height here. If I'm estimating weight, it's weight. If I'm estimating money, it's money. And what we do to show it's a prediction is we throw a hat on it. Right here, this thing's called a hat. And so that's y hat, or y unit prediction. And then it equals your y-intercept, which is also sometimes called the constant, plus your slope, times the x unit. So you have to write it in context. So, you know, in elementary school or middle school or wherever, even sometimes in high school, you guys do the standing long jump. And so what that would be is jump is equal to, let's say it's 2.67 plus 1.3 times your height. So my x values were height, my y values were jump, and this is the equation I would make. So you don't ever write x and y, we actually write the units. Okay, so how to describe slope. This is kind of an important thing. You're going to have to do this a lot. Let's highlight these. And we want to make sure that we understand it. And so what I've done is I've kind of created a sentence stem that you can use over and over. And so it's the blank increases or decreases, and you have to circle one of those. Blank for each additional blank. And now here's the most important thing. It has to be on average. You got to remember that part. Okay, so what happens is the y unit increases or decreases whatever the slope number is for each additional x unit on average. So if I'm interpreting this, the jump length increases, because that's a positive number, 1.3 inches for each additional inch in height, because that's height on average. Now the reason you have to add on average is otherwise people will think that it always does that. And remember, scatter plots are kind of up and down. Sometimes it's exact, sometimes it's below. So by adding that on average, it makes it so it's not exact. Okay, so now there are some conditions in order to be able to use an equation like what we just did there. And there's 4 of them. There's the quantitative condition, and so they both have to be quantitative variables. And remember, quantitative variables are measurements. There can't be any strong outliers. You can have some, like one outlier, but it's kind of close. But what you would do is we'd say we are going to proceed with caution. Is it straight enough? Does it look linear? And then, does the plot thicken? This needs to have consistent spread. So essentially what that means is, let's say I have a graph, and at the beginning the points are kind of far apart, but then as you go up further, they get closer together. So what it kind of looks like is a tornado, right? If I actually draw this out, this actually kind of looks like a tornado, a funnel of a tornado. We don't want that. This is bad. This is the plot thickens. Bad. Okay? We don't want it to thicken. It doesn't matter if it thickens here, thickens on the left, thickens on the right. We want it to be consistent or equal spread throughout the whole graph. Okay? These two right here, we prove that something's straight enough and that the plot thickens by doing the residual graph. Okay? We're going to look at the residual plot. And what the residual plot is, the residual plot is it graphs the residuals. So let's do it this way. It graphs the x values, comma, its residual. It graphs all of those. So it graphs the x and then how much above or below the line it is. We want this to be random. That's super important. Residual graphs are actually where you'll really see whether there's a curve. Okay, so to find residual graphs in the calculator, the first thing you must do is you have to enter data in L1 and L2. You can't do it without having the data in there. The second thing you have to do is you have to find your equation. So you have to run stat calc number 8. That's going to find the residuals because it gives you an equation. And then the third thing you're going to do is you're going to graph. So you're going to do second. I should hit that button. Stat plot. And you're going to do a scatter of L1 and resid. Okay? So I'm going to kind of show you what this looks like. I have my data in L1 and L2, so I have to go stat, calc. I go down to number 8. Make sure it's zoomed in. I hit enter. I want my data in L1 and L2. Okay, so it gives me all my information. It gives me my equation. And so now I can graph it. So I'm going to do second stat plot. So second y equals, which is stat plot. Right now I have a box and whisker, which I want to do a scatter. And I have to go here, and I need it with L1 and resid. The way I get resid is I'm going to use this key right here. You see how it says list? I'm going to hit second list, and I can go down and find resid. And now I'm going to hit graph. Now I can't see it. Oops, I got a line in there. Let's take, oh, I got lines in there. I got to take care of those. Let's get rid of those. Don't want any lines. So let's graph it again. I don't see anything. So I go to zoom, and I go down to number 9 because that is zoom stat. And that's going to fit my window for my statistics. And that is my residual plot. It kind of looks a little curved, right? It looks curved with an outlier. So that looks like it might be an outlier. If it's curved, maybe we can consider it random. This would be one that I'd be worried to move forward with. If I were to move forward, I would say I'm going to proceed with caution. Okay, so you have residuals, which is observed minus predicted. You have the equation, and we'll talk about the 3 different ways you can get the equation later. You interpreting the slope, checking conditions, and then checking your residual plot. Okay, so these are all key things for being able to do linear regression.